All right, assalamu alaikum everyone. Let's begin. So we started P3 integration in our last session. Now, what have we done until now? We have talked about how to integrate power functions. So we've done that in paper one already, in fact. We had a look at this, and then we talked about exponential functions, sine, cos, and secant square. We talked about their integrals. So this is how their forms used to look like. We did some examples in this, and we said it's important that whatever comes in place of x here in these rules, that is linear. If it's not linear, we cannot use these rules like this. All right, so whatever comes in place of x here, it has to be of this form ax plus b when you're doing integration. And then whatever it is, you have to also divide by the derivative of that while you are integrating. So we did these rules yesterday. If the expression inside is not linear, for example, you have x squared plus 1 like this, the rule does not work. You cannot integrate like this. Okay, so that's what we did in the last session. Then we talked about integral of 1 over x and anything that looks like this, where the derivative of the denominator is in the numerator. Okay, so when numerator is the derivative of the denominator, its integral is going to be log of the denominator. So this is one very major rule for integrating fractions. Whenever you have a fraction, this is one of the first things you think about. That do you have this form? That do you have the derivative of the denominator in the numerator, or can you make the numerator the derivative of the denominator somehow by multiplying or dividing by a constant? We did this yesterday. We did some examples in this as well, and we also learned that tan is also integrated using this particular rule, because when we integrate tan, we say it can be written as sine over cos, and then we could convert it to that form and find the integral of that. Now, while we do this, we have to keep this thing in mind, that when we are multiplying or dividing to convert something in that form, where the derivative of the denominator is in the numerator, we can only multiply, divide by constants, not by x. All right, so we can't multiply and divide by x like in this example. If we do that, that would be wrong, and it would not give us the correct integral. All right, so we can only multiply and divide by constants, not by variables. All right, so that's what we did in our last session. Now let's move on and discuss the next rule that we have now, and that is the rule when something is in a form that can be converted to tan inverse. So this is the next rule that we have to do now. So in the formula sheet, another rule that you're given is like this. If you have a function f of x, its integral f of x dx is 1 over a tan inverse of x over a. So if you have something of this form, 1 over x square plus a square, its integral is given by 1 over a into tan inverse of x over a. All right. For instance, if I have something like this, if I have 1 over x square plus 4, and I want to integrate this. Now compare it with the form that's given there. I have 1 in the numerator, x square in the denominator as the first term, and then I have 4. In place of 4, they have a square. If I were to convert it to something like this, that I have 1 over x squared plus 2 squared. So I could write 4 as 2 squared. Then if I compare it with that form, I can see that in place of a, I have 2 here. And now this is exactly the form that we have in this rule, that if we have 1 over x squared plus a squared like this, it can be integrated and converted to this form. So what would this become? In place of a here, you can see what's the value? I have 2. So in this form here, I can just input a equal to 2, and that would give me 1 over 2 into tan inverse of x over 2 plus c, and that would be my integral. All right. So this is the rule that in which we convert something to tan inverse. All right. So this is the next rule that we have. It's written in the formula sheet in this form: 1 over x squared plus a squared. If you have something in this form, it can be converted to tan inverse like this. All right. Now, there's a condition here. If you use this form like this, the numerator can have any constant basically. So, let's actually take another example before I tell you the condition. So let's say if I have something like this, 2 over x squared plus 4. If you remember, this was an example that we did yesterday. 2 over x squared plus 4. We tried to do this using logs, but we realized we would have to multiply and divide by x in that case. So the log rule did not work here. We could not really integrate it like this. So we could not integrate this yesterday using the log rule. However, it turns out this is actually the form that can be converted to tan inverse after integration. So if you had something like this, 2 over x squared plus a squared, so 2 over x squared plus 4, you have to integrate this thing. Now, compare it with the form that's given there. It's very similar to that. The only difference is that in the numerator, in place of 1, you have 2. Now, 2 is just a constant. What you can do is you can actually write 2 outside the integral, right? 2 is being multiplied here. So you could write this thing as 2 into integral of 1 over x squared plus 2 squared. Now, 2 is just written outside here. Inside the integral, we've got exactly that form. In place of a, we've got 2. So when we integrate this, this is going to become 2 into 1 over 2, right? Using this, 1 over 2 into tan inverse of x over 2 plus c. And if we simplify this, 2 into 1 over 2, that's going to get cancelled. And we're going to be left with tan inverse of x over 2 plus c. That's the integral for this. All right. So in the numerator, if you have some other constant in place of 1, all you have to do is just write that outside the integral, and you can just integrate it like this. So in the numerator, you could essentially have any constant, and that doesn't matter. So you could have any constant in place of 1. You can still integrate it. You will just write 1 outside the integral, that constant outside the integral, then apply this rule. Okay, so whatever constant you have here, that could actually come in place of 1 here. All right, so I could actually write this rule like this on the side. In the numerator, it's not necessary to have 1. You could have any constant. And if you wanted to integrate this, this would turn out to be k over a into tan inverse of x over a. Okay, so it's the same thing. In place of 1, you could have anything else as well, any other constant as well, and that this rule would still work. All right, now that's one condition that we have while using this rule. There's another condition that's very important to remember, and that is that in the denominator here, we have this x squared term. Now this x squared term needs to have a coefficient of 1. It cannot have any other coefficient apart from 1. If it's something other than 1, you'll have to make it 1 somehow if you want to use this rule like this. So so let me just write that down here first of all. The coefficient of x square must be 1 here. You can't have another number with this. You can't have 2x square or 3x square here in place of x square if you're using it in this form. Okay. So if you're using this form, the coefficient of x square, it must be 1. All right. So these are two things that you need to remember. Now let's take another example. So we looked at two examples already. We have something now. For instance, we want to integrate -7 over x squared plus 3. We want to integrate this with respect to x. Now, again, let's compare with the form that we had there. Just copy that here. So we have this in front. This is the form that we have. Now, is this the form on the left side? Well, we have a constant in the numerator, so that's okay. We have the coefficient of x squared, that is 1. That's also fine. But the constant has to be in this form a square. What we can do is we could write -7 outside if we want. Then inside, we would be left with 1 over x squared. Now, 3 needs to be written in the square form. Okay, so we could say 3 is square root of 3 whole squared. And that's the same thing, right? So 3 could be written as square root of 3 whole square. And now if we compare with that form, in place of a, we have square root of 3. So the value of a that we have here in this form is square root of 3. Now we can just use this rule and say the integral turns out to be -7 multiplied by 1 over a into tan inverse of x over a. That becomes 1 over square root of 3 into tan inverse of x over square root of 3. And that would be your integration. -7 over square root of 3 into tan inverse of x over square root of 3. This is the answer that we get from this. All right, so this is how this tan inverse rule works. Okay. All right, let's take another example. Let's take another example. And now let's say we have something like this. We have 6 over 3x squared, or let's say 4x squared plus 2. You've got something like this. And that's going to get simplified. In the numerator, let's say I have 5 instead. 5 over 4x squared plus 2. I want to integrate this thing. Now, again, let me just copy that form here. So we have that in front. And see how we can use that now. All right. Remember the condition? The coefficient of x squared has to be 1. It's not 1 here. All right. The coefficient of x squared is not 1. So what do we do with this? Now, you have to make it 1 before you can use this rule. Otherwise, you can't use this rule. How do you make the coefficient of x squared 1 here? What you can do is you can say, let's take 4 common outside from the denominator. So first of all, you can write 5 outside anyway from the numerator so that you have 1 inside. In the denominator, take 4 outside, take 4 common from this. If you take 4 common, what are you left with inside? X squared plus 2 over 4, right? So when we take 4 common from this thing, that leaves us with x squared plus 2 over 4, which could be written as x squared plus 1 over 2 essentially. And now we have something that is very similar to this form. We have x squared here. We have 1 in the numerator. And we have 1 over 2. We could write 1 over 2 as a square like this. We could say It's 5 over 4 outside, and inside we have 1 over x squared plus square root of 1 over 2 whole squared. And this is what we want to integrate now. Compare with the form that's given there. What do we have in place of a? In place of a, we have square root of 1 over 2. We just have to replace a with square root of 1 over 2. Okay, so outside we have 5 over 4. That remains as it is. Inside, let's apply this rule now. 1 over a, what's the integral of this? 1 over square root of 2, or like this, 1 over 2 square root, right? 1 over a into tan inverse of x over 1 over 2 whole square root. That's what the integral looks like. You could simplify this slightly. This 2 is going to go to the numerator. Similarly, this 2 is going to go to the numerator. So it becomes 5 over 4 into square root of 2 into tan inverse of square root of 2 times x in this case. We could simplify this slightly more, and this becomes 5 square root of 2 over 4 into tan inverse of square root of 2 times x plus c. That is the integration of this expression. So this is the most complicated scenario you could have here, that you have some coefficient with x squared. If you have a coefficient with x squared, you'll have to take that common outside and then make the coefficient of x squared 1. Once we're done with that, you can just work with it like this. Okay, so convert it to that required form, and it gives you the result. Okay, I hope that makes sense. So this is one rule that we have for tan inverse. This is one rule that we have for tan inverse. Now, there's another rule that is simpler in some particular situations. So in the formula sheet, you're given this rule, right? So this is the rule that you're given for integration in the formula sheet. Let me actually show that to you quickly as well. This is how the formula sheet looks like. Okay, something went wrong with this. Okay, so this is the integration page on the formula sheet. All right, let me actually just copy this here. We'll need this later as well. This is the whole page that you have for integration in the formula sheet. And you see, this is the formula that you are given there. For tan inverse form, 1 over x squared plus a squared, that is 1 over a into tan inverse of x over a. For tan inverse, this is a rule that we're given in the formula sheet. Okay. But remember, we've done another rule in paper in differentiation earlier, and that was for differentiation, that if you have tan inverse of x, how can you differentiate it? Tan inverse of x, the derivative of this is 1 plus 1 over 1 plus x squared. And if you have something other than x here, what do? You also have to multiply by the derivative of that expression like this. Now, integration is reverse differentiation. Integration is reverse differentiation. What we could do is we could say, let's just use this idea that we did in differentiation earlier. So this is the rule that we did in differentiation. that if you have y equals tan inverse of something, the derivative of that is going to be dy over dx is going to be 1 over 1 plus square of that thing, and then you multiply by the derivative of that. All right. If we were to reverse this and say, if we have something in this form, 1 over, or let's actually write this together, this is going to become derivative of that thing divided by 1 plus square of that thing. If we had to integrate this expression, this would give us tan inverse of this thing, whatever there is in that box, plus c. This is another rule that you could actually use. Now, this is ongoing on here. I'll quickly explain how to use this in a moment and why to use this in a moment. Let's take a 1 minute break and then resume after that. All right. So this is the first rule that we have done. And remember, this is a rule that can be applied on any such integral. This will always work. So if you understand this and you think you can always use this, that's perfectly okay. This will work for all integrals that can require you to convert something in the tan inverse form. This is given in the formula sheet as well. You could always use this and it'll work in every case. Okay, so what we've done until now for tan inverse, if you understand this, you can integrate all functions that have to be integrated using tan inverse. You could do that. Okay, keeping in mind that the coefficient of x squared should be 1 here, you could use this. Okay. However, sometimes it's going to be quicker, at least slightly, to use this other form. So we could use that idea that we had from differentiation. We could use that to integrate one particular type of the tan inverse form slightly quicker. For instance, if you have something like this, if you have 7 over 4x squared plus 1, and you want to integrate this thing. You want to integrate this thing. Now, if you were to use the earlier form for this that we did above, remember the condition for that was that this thing, the coefficient of x squared, it has to be 1. So you would first need to take 4 common outside. That will leave you with 1 over 4 here. Then you write that in square form and then use that rule. And that's okay. That will work. That will give you the correct result. But another idea here could be that we could use this rule directly. Why is this going to work directly? Because in this rule, the condition is that one of the terms needs to be 1. One of the terms needs to be 1. And the other term here, it could be anything. So in the denominator here, you see, one of the terms is 1, and the other term is anything else. That doesn't matter. As long as you have the derivative of this thing in the numerator. So if you can convert it to that form somehow, that whatever is being squared here, you have the derivative of that in the numerator, you could use this form. Now, let me explain how this would work here. In the numerator, so in the denominator, what we have is 4x squared plus 1. Let's write it in this form. 1 plus something squared. How could we write it? We could say this is 1 plus 4x squared. If we just interchange this. 4x squared, can this be written in a square form? We could say this is 2x whole squared. So we have written this in a square form. All right. In the numerator, we have 7 right now. So denominator is in this form now. 1 plus something squared. All right. Now, what do we want in the numerator in this case? In the numerator, we want the derivative of this thing. Derivative of 2x. What's the derivative of 2x? The derivative of 2x is 2. So we want 2 in the numerator here. How can we have 2 in the numerator? 2 is just a constant. So what we can do is we can say, let's write 7 outside. Let's take 7 outside. And now since we need 2 here in the numerator, we could write 2 here. And then to balance that, we could have 2 divided outside the integral. And now inside the integral, you've got exactly the form that you have here. And you could write down this integral directly. Since it's this form, the integral is going to be tan inverse of this box. What do you have inside that box here? 2x, so 7 over 2 into tan inverse of 2x. That is your integral, and that will give you the final result like this. So it's just 3-step process in this case. Why does this work quicker in this case? Because one of these terms is 1 here. When you have a tan inverse form in which one of the terms is 1, using this rule is going to be slightly quicker. So let me write that here. You can use this form. Again, you can use this form. It's not necessary. You could just do everything using that earlier form as well, and that's perfectly okay. But this makes it slightly quicker in this particular case. So you can use this form when one term in the denominator is already equal to 1. Okay. In this case, using this rule would be slightly quicker. Now, if you were to use the other rule in this, that would also be okay. That's perfectly okay. That will still work. Let me explain you how that would work here as well. So you have 7 over 4x squared plus 1. You integrate it with respect to x. What was the earlier rule? Let me copy that here. This is the one that you're given in the formula sheet and on the integration page. What was the condition for this? The condition for using this form was that you need the coefficient of x squared to be 1. So for that, you would need to take 4 common outside from the denominator. So you could write 4 outside in the denominator as well. You can write 7 outside from the numerator. Inside, you're left with 1 plus x squared plus 1 over 4. All right. And now, the coefficient of x squared in the denominator is 1. You need to write down the second term in a square form. How would you do that? It becomes 7 over 4 into integral of 1 over x squared plus 1 over 2 whole squared. So you have this in squared form now. In place of a, what do you have? You've got 1 over 2. So a equals 1 over 2. You can just input a equal to 1 over 2 in this form on the right side. So the integral of this therefore becomes 7 over 4 into 1 over a, that's 1 over 1 over 2, into tan inverse of x over 1 over 2. Now 2 goes to the numerator there. It becomes 2 into tan inverse of 2x. 4 and 2 get cancelled. You're left with 7 over 2 into tan inverse of 2x plus c. This is how it would work using that earlier rule. That gives you the same result as well, although with a couple of more steps, couple of extra steps, but you get the same result from this as well. So you could also use that earlier rule like this. Okay, but it's slightly longer. So in this case, and only in this case, when one term in the denominator is already 1, you might save a minute or two if you use this other form. Okay, so if you get that, that's great. Otherwise, this will work every time, and that's okay as well. Okay, so you have to know this for sure. This is necessary for you to know. You must know this. This is given in the formula sheet as well. You must know when you're using this, the coefficient of x squared has to be 1. You could use this every time. And this is kind of optional. This might save you some time if you know that one term is already 1. This might make your working slightly quicker in that case. All right, any quick questions on this? Because this is what we have in the tan inverse form. We want to move on now and discuss the next concept. Let me know if there's any problem with this. Okay, so if there are no questions, let's move on. So again, keep in mind, so you have to build a mapping in your head now. What have we done until now? We have learned how to integrate these simple expressions. Then we learned how to integrate fractions. The first rule that we have for fractions is this one. This is the first rule for fractions. If the derivative of the denominator is in the numerator, you can convert it to log form. That's the first way, the first method for integrating fractions. The second method for integrating fractions is this rule where you have where you have the integral converted to the tan inverse form. Okay, this is the other uh, method for integrating fractions. This is what we've done. All right, and now we want to look at what happens if none of these two forms applies. Okay, all right, so these are two ways of integrating fractions using the log rule and the tan inverse rule. For the log rule, what was the condition? The condition was you need the derivative of the denominator in the numerator. For the tan inverse rule, what is the condition? You need something in this form. 1 over x squared plus a squared. It has to be of this form. Okay, so you need a plus in the middle. That's important. You can't have a minus here. You need a plus. And you have only two terms in the denominator, one x squared and one constant. And in the numerator, you have a constant. Okay, so in the numerator, you need a constant. In the denominator, you need x squared plus a constant. That's the tan inverse form. Okay, so these are two methods for integrating fractions. Now, let's move on. Let's move on. And let's say we have something in this form now. Integral of 14 over x plus 2 into 2x minus 3, for instance. Let's say we want to integrate this thing. All right. Now, what form is this? Is it, do you have the derivative of the denominator in the numerator? Well, we don't. In the denominator, we have a quadratic function. If you were to differentiate it, you would actually get something linear, something in terms of x. In the numerator, you have a constant. So the log form does not work here. Even if you were to simplify this, you can try simplifying it. In the numerator, you have 14. In the denominator, you're going to get 2x squared plus 4x minus 3x, which is plus x minus 6. That's what you would have in the denominator in simplified form. What's the derivative of the denominator? It's 2x plus 1. You can't have 2x plus 1 in the numerator anyway. You would have to multiply by x. That's not allowed. So you cannot have the derivative of the denominator in the numerator. That form doesn't work. All right. What about tan inverse? It's not tan inverse form either. In tan inverse, you need x squared plus a constant. You can't have an x term in tan inverse. It's not the tan inverse form either. So both of those rules do not work. Okay. Both of the rules that you've done for fractions, they don't work on this. So what do we do in this case? The third option that we have for integrating fractions is that we break it down into partial fractions. So if we have some factors in the denominator like this, if the denominator is in factorized form like this, you can break it down into two parts. You can break it down into its partial fractions and then integrate those separate fractions one by one. Okay. Now, the fraction that you have is 14 over x plus 2 and 2x minus 3. Okay. You first find partial fraction for this. Remember, we've done partial fractions. So this is two linear factors in the denominator, and they're both different. Non-repeated linear factors. The form that you have for this is a over x plus 2 plus b over 2x minus 3. You would find partial fraction for this, right? So we've done this before. Find the partial fractions. Let's say they turn out to be, in this case, in fact, let me actually just figure this out quickly. Okay, so since it might trouble you if you don't know how to find partial fractions, because we'll need to do that again and again, let me actually just go through this process here again in case you've forgotten. So what you can do is just multiply this denominator on the right side. That gives you 14 identical to a into 2x minus 3 plus b into x plus 2. And now we input some specific values of x here. We could input x equal to 3 over 2 first of all. Let's see what that gives us, because that's what makes this bracket 0. So why are we inputting this? We basically see what value makes this 0. So 2x minus 3 equal to 0. That gives us x equals 3 over 2. We could input 3 over 2 here in this identity first of all. So that gives us 14 equal to a times 0, the first term becomes 0. The second term has b into 3 over 2 plus 2. And that gives us 14 equal to 7 over 2 times b, and b turns out to be 4 in this case. All right. Now, how do you make the second bracket 0? X plus 2 equal to 0. We can input x equals minus 2 here. Let's see what that gives us. Let's input x equals minus 2. And from that, we have 14 equal to a into 2 times minus 2 minus 3 plus b into 0. That term becomes 0. And we're left with 14 equal to minus 7 times a, and a is equal to minus 2. So we have found the partial fractions. And now once we have the partial fractions, we can say that integral that we were looking for, integral of 14 over x plus 2 into 2x minus 3 this integral can actually be converted to something like this. The partial fraction for this, a is minus 2, so that's minus 2 over x plus 2, minus 2 over x plus 2, plus b over 2x minus 3, b is 4, so that's 4 over 2x minus 3. You could convert that integral to partial fraction form like this. So you had one fraction, you broke it down into two separate fractions. And now you can just integrate these two fractions separately. One fraction is minus 2 over x plus 2. Integrate this thing separately. And the other fraction is 4 over 2x minus 3. Integrate this separately. Now, how do you integrate these two fractions? Now you use one of those two rules that you've done before. Minus 2 over x plus 2. Is this the log form or the tan inverse form? Can we use any of them here? Well, it's not the tan inverse form because we don't have a square in the denominator. So tan inverse form does not work here. We don't have x square. What about the log form? Do we have the derivative of the denominator in the numerator? What's the derivative of the denominator? Derivative of x plus 2 is 1. If we have 1 in the numerator, we could convert it to log form. So all we have to do is just write minus 2 outside the integral, and inside the integral, we would be left with 1 over x plus 2. And now this is the log form. What about the second one? 2x minus 3 has a derivative that is 2. So we want 2 in the numerator. What we can do is we can say, let's take 2 common from 4, and we have 2 left inside. In the denominator, we would have 2x minus 3. And now this is also the log form. So what's the integral then? The first one becomes minus 2 into ln of the denominator, which is ln of x plus 2, plus 2 into ln of 2x minus 3 plus c, and that is the integral of this expression. All right. So if we have something like this, in which we have factors in the denominator like this, we can break it down into its partial fractions first of all, and then just integrate those fractions separately one by one. Okay. So that's the third method that we have for integrating fractions. Okay. Keep this in mind now. When you're integrating fractions, the first thing you could think about is, does the log rule apply? Is the derivative of the denominator in the numerator? Well, if it doesn't work, does the tan inverse rule work? Do you have the form in which you have some constant over x squared plus a squared? Do you have that form? If not, then think about, can you find partial fractions of the fraction? That's the third possibility now. If you can find partial fractions, you can find partial fractions first of all, and after that, apply either the log rule or the tan inverse rule. Okay, so this is a third possibility that we have for fractions now. We'll have more. We'll discuss them tomorrow, inshallah. But before we end, let's do one more example in this. Let's do one more example in this. Now, let me actually take an example from somewhere. that I know the partial fractions for, so we don't have to do that whole process again. Okay, I'll have to give you a minute to try this as well. So let's say we have a fraction like this. 10x squared plus x plus 1 divided by 2x minus 3 into x squared plus 4. We want to integrate this fraction. All right, we want to integrate this fraction. Now, does any of those rules apply here? The log rule, the tan inverse rule? It's very clear it's not the tan inverse form, right? Because tan inverse form only can only have two terms in the denominator, one x squared term, and then plus some constant. It's not that form. What about the log form that we have the derivative of the denominator in the numerator? We could check that. If we were to simplify the denominator, that would give us 2x cubed minus 3x squared plus 8x minus 12. Simplifying the denominator would give us this. Now, what's the derivative of this thing? The derivative of this is 6x squared minus 6x plus 8. Can we have that in the numerator somehow by multiplying or dividing by a constant? Well, we can't. All right. So we can't have the derivative of the denominator in the numerator here. So the log rule does not work. Now, if the log rule does not work as well, what do? Can we find partial fractions? Well, we have factors in the denominator. We can find partial fractions for this. What is the form going to look like here? 10x squared plus x plus 1 divided by 2x minus 3 into x squared plus 4. The partial fractions for this are going to look like this. A over 2x minus 3 plus, the second factor is a quadratic factor. This would be bx plus c divided by x squared plus 4. All right, this is how the partial fraction form is going to look like. Now you convert it to this. So you basically find partial fractions for this. So let's say you do this and find the values of a, b, and c. Take, in fact, I think I'll just write down the values of a, b, and c directly here. Let me just check what the values of a, b, and c here should be. So you apply this whole partial fraction process, right? We've done this in detail before. Find partial fractions for this and see what that turns out to be. In this case, the partial fractions are going to turn out to be a equal to, so the value of a is going to turn out to be 4. So when you find partial fractions, a will be 4, b will be 3, and c will be 5. All right, so you do this whole process, find partial fractions, you'll get this at the end. What that means is this integral that we had written there, (10x squared plus x plus 1 whole divided by 2x minus 3 into x squared plus 4, and then integral of this with respect to x. This could be broken down into two separate fractions like this. We could say it's the integral of a over 2x minus 3, which is 4 over 2x minus 3. Integrate this separately. And the second integral is bx plus c, that would be 3x plus 5 divided by x squared plus 4. These are the two fractions that you get from this after doing partial fractions. All right, so you just write them separately like this, and now you have to integrate these fractions separately. Now, let's think about these two fractions. Let's think about the first one. Does the log rule work here? Well, what's the derivative of the denominator? 2x minus 3. The derivative of 2x minus 3 is 2. So you want 2 in the numerator to be able to use the log rule. Can we have 2 in the numerator? We can take 2 common outside. Inside, we would be left with 2 over 2x minus 3. And now this follows the log rule, the log form. the derivative of the denominator is there in the numerator. So what's the integral for this? It's ln of 2x minus 3. That's the integral of this thing. All right. So that's pretty straightforward, the first one. Let's look at the second one now. 3x plus 5 over x squared plus 4. Now think about that. Does the log rule work? What's the derivative of the denominator? The derivative of the denominator is 2x. In the numerator, we have 3x plus 5. Well, it doesn't work. So we can't multiply 3x plus 5 or divide anything by 3x plus 5 or multiply anything by 3x plus 5 to get 2x. It doesn't work because we also have a plus 5 there. So the log rule is not going to work here. Well, what about the tan inverse rule? Remember, for tan inverse, we need a constant in the numerator. Yes, the denominator follows that rule. X squared plus a squared, that's what you have in the denominator, but numerator has to be a constant to be able to use the tan inverse rule. The numerator here is not a constant. So tan inverse also does not work here. Tan inverse also does not work here at this point. Well, what do we do then? Do we find partial fractions of this as well? We can't, because we don't have any factors in the denominator. We don't have any factors in the denominator. It's a single expression. X squared plus 4 cannot be factorized. X squared, if it was x squared minus 4, we could write that as x plus 2 into x minus 2 and then find partial fraction for that. That would work. But this is x squared plus 4. We can't do anything with this. So the partial fraction rule also does not work. So what do we do now? There's another possibility, and that's the fourth method of, that's not really a method as such, but that's a trick that we use here. And that is that we break the numerator down. We have two terms in the numerator. What we could do is we could say, let's write 3x over x squared plus 4 separately, and then 5 over x squared plus 4 separately. So break the numerators down like this. So remember that rule, that algebraic rule that we have. If we have a plus b over c, that's the same thing as saying a over c plus b over c. So we're just writing those two terms separately like this. Okay, 3x over x squared plus 4 plus 5 over x squared plus 4. So we broke that fraction down using the numerator. So we broke the numerator down. In partial fractions, we break the denominator using these factors, right? So we break down the denominator. But now we only have a single denominator here. We don't have any factors in the denominator. So in this case, what we say is, let's break the numerator down. So it's 3x over x squared plus 4 and 5 over x squared plus 4. How do you integrate these expressions now? Let's look at the first one. Can we use the log rule here? Well, the derivative of the denominator is 2x. Can we have 2x in the numerator somehow by just multiplying or dividing by a constant? Well, in this case, we could. What we could do is we could say, let's write 3 outside. That's just a constant, right? Inside, we would have x squared plus 4. Now, what do we want in the numerator? We want 2x in the numerator. That's the derivative of x squared. Derivative of x squared is 2x. So we want 2x in the numerator. What we can do is we can say, let's write 2 here in the numerator. But to balance that, we also have to divide by 2 outside. So we multiply by 2 inside and divide by 2 outside to balance that. And now inside the integral, we have the log form. So this could be integrated like this. We could say this is 3 over 2 into ln of x squared plus 4. So we've integrated this part as well. Now, what about this fraction? 5 over x squared plus 4. Is this the log form? Well, what's the derivative of the denominator? It's 2x. Can we have 2x in the numerator? We can't, because we would have to multiply by x. So the log rule does not work. But isn't this the tan inverse form? You have a constant in the numerator and x squared plus a constant in the denominator. The tan inverse form looks like this. the integral of 1 over x square plus a square is given by 1 over a into tan inverse of x over a. So we have a constant in the numerator. We could write that constant outside. Inside, we have 1 over x square plus 2 square. And this is the tan inverse form. A is basically 2 here. If we were to integrate this, we would get 5 as it is. That's multiplying outside. Integral of this thing is 1 over 2 into tan inverse of x over 2. All right, then you have a plus c after that. So what's the integration of this whole thing then? It's 2 ln of 2x minus 3. That was coming from that first fraction already. And then we have this thing. We could write down the final result like this. 2 ln of 2x minus 3 plus 3 over 2 into ln of x squared plus 4 plus 5 over 2 into tan inverse of x over 2. And that is your integral. Now, there's another thing that you also need to do in such cases. In the final answers that the examiner is looking for, the final answer that the examiner wants, they want a single log term. You generally cannot have multiple log terms in the final result. So you'll also have to use some log rules here to make it a single log term. What you can do is you can say, let's take this 2 to the power. So it becomes 2x minus 3 whole squared, like this. Let's take this 3 over 2 to the power as well. This goes here, using the power law of logs, right? So ln of x squared plus 4 whole raised to the power 3 over 2. And then we can use the multiplication law to make it one single log term so that it becomes ln of 2x minus 3 whole squared into x squared plus 4 whole raised to the power 3 over 2 plus 5 over 2 into tan inverse of x over 2 plus c. That would be your final result in this case. So this was addition outside log, which becomes multiplication inside the log. That's the multiplication law of logs. That's what we can do here. This is the integral of this expression. All right. So this is the fourth way you could integrate fractions. Sometimes you have to break the fraction down into two parts from the numerator. Write the two terms separately from the numerator, so it becomes 3x over this, and then 5 over this. Integrate those two fractions separately like this. Okay. So I'll summarize all of this in the next class. In fact, I'll summarize all of this in the next class, and then we will learn one more method, or in fact, one more method for integrating fractions, and we will do some practice questions after that on whatever we've done until now. All right, so we did two things today. We did two new methods for integrating fractions. The first was using integrating fractions using tan inverse form. This was the first form, and that works when you have constant in the numerator. So you need a form like this. So if you need to remember that, if you have something like this, constant over x squared plus a square, this thing can be integrated using tan inverse. Okay. You can actually just show that to you quickly right now before we end. So it sort of, stays in your head, hopefully. Okay. So for integrating fractions, now ignore everything else for now. So I'll just get rid of this. So ignore this for now. And just focus on this part for now. For integrating fractions, this is the first rule. If you have the derivative of the denominator in the numerator, that can be converted to the log form, ln form. If you have a form like this, constant over x squared plus a square, you have constant over x squared plus a square, that converts to the tan inverse form. All right. And Another possibility is that you find partial fractions, and then after finding partial fractions, you use either the log form or the tan inverse form. That's another possibility. Okay. And then another possibility is that you break the fraction. For example, if you were integrating x plus 1 over 2x, so rather than finding partial fractions, because partial fractions breaks the denominator, if you can't break the denominator, think about whether it would help to break the numerator down. So x plus 1 over 2x, you could write that as x over 2x plus 1 over 2x, and then just integrate those two things separately. All right, so these are different ways of integrating fractions that we have done until now. All right, we will do more tomorrow, and then we'll do some practice questions as well. Okay, before we move on to the next concept. That's it for today. If you have any quick questions, you can let me know. Otherwise, I'll see you again tomorrow. Allah Hafiz. Okay, so I'm assuming there are no questions. All right. Allah Hafiz then. I'll see you again tomorrow.